All right, children, let's go over the test review, our last test before Christmas break. That way we will be completely done with everything and you will have no homework for the week. So that's good. So let's get started on the test review. So what to study? I would definitely study your worksheets from the homework that we've done the last couple of weeks. I would study your notes all the way from the history of the periodic table, so like with Mendeleev on them, and all the way to day 4 notes. So day 1 through day 4 notes and homework study. And then the questions will be like the last test where there's matching at the top, multiple choice, and then trends, and then short answers. So the test will not, the structure of the test will be the same. So we're just going to go through again, like I've been telling you in class. This test is not like the electron configuration test. It is more vocabulary. You need to know the 3 trends. You will not be able to have a cheat sheet, unfortunately, just because of the nature of this test. If you have a cheat sheet, there's really no way to fail. So you guys just have to kind of practice these trends. So the first type of question are fill in the blanks for the review. So we're just going to go through them and I'll kind of explain if I feel like they need an explanation. I have a periodic table next to me. I'm not sure what else I'll need, but I think we're good. All right, so first one, a vertical column on the periodic table is called a what? So these columns down here that go down, those are called groups. You guys should, that should be easy for you. So groups, okay? The periodic table was first arranged by the scientist. We're going to call this one Mendeleev. I'm sure I'm saying it wrong too, but whatever. All right, now question C. The elements in the periodic table are presently arranged in order of increasing what? So remember on the notes, the first guy, he arranged them by atomic mass, but remember that could present a problem due to isotopes. So now so mass can change, as you know, but what doesn't change are the number of protons. So that's why we do it, we arrange them in order of increasing atomic number, not atomic mass, but atomic number. Okay, the blank says that when the elements of the periodic table are arranged in order it's actually supposed to be of, that's been bothering me, of increasing atomic number, there are periodic patterns in their physical and chemical properties. So as they increase in atomic number, so 1, and then helium is 2, and then 3, 4, blah, blah, blah. So these guys all have 1 valence electron. These all have 2. Remember I showed you a video of these reacting in water. They're very violent. These guys have a similar property. You should know those. The noble gases, they're very stable because their valence electrons are, their valence orbitals are full. And then these like to accept an electron. So they all have similar properties according to their group. So that's again why the periodic table looks the way it does. So we're going to say the periodic law is the answer. It's what we notice. It's basically the fact that we notice these trends in the periodic table. It's how we've made the periodic table. All right, E, all the elements in group 17 will have a blank configuration in their outermost energy level. So again, group 17, remember the groups are vertical. So group 17 will all have a what configuration? And remember electron configurations is the 1s2, so on. So this is the P block. And all of these, so we can't like label an energy level because it could be 2, it could be 3, 4, or 5 energy level. So what we do know is all of these in this group, they will be a P, okay? They will have a P, and it is P1, 2, 3, 4, 5. So they will have a P5 configuration. So in group 17. That's how you answer those. Okay, group 1 is also known as the what metals? So this is directly from your notes. So group 1 is known as the alkali metals. Okay, the second rows of the bottom of the, at first I thought I didn't push record. I was about to be a little frustrated. The two rows at the bottom of the periodic table are also known as the what block? So, let's see. So these two rows right here, you guys know that this is the S block. This is the D block, okay, those transition metals. And then this whole block right here is P. And this should be a very easy question for you. That's the F block, okay? So the answer is the F block. Very easy. Okay, so all of the elements in group what have an electron configuration that ends in P2. So if you look at the P block, P2, so this is all P1, this is P2. So all of the elements in group 14 are P2, okay? So all elements in group 14 have the configuration that ends in P2. Very easy. The D block elements are also known as the, again, sorry guys, but most of this test is vocabulary. All of these are called transition metals, okay? Remember, these are representative, the S and P. These are transition, and these are intertransition metals. Okay, transition metals. There's more than one. Okay, so the elements in group 12 have a what electron configuration? So all you do to find this out, you find group 12, which is right here. Okay, so this happens to be in the D block. Okay, so have a D. Let's look at what number in D. So we're group 12. So you could just know that that's D10, or you would count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's D10. So they all will have a D10 electron configuration. Next question, an atom with a positive or negative charge is called an ion. You guys have actually had this on a test before, so this should be easy. It becomes charged when it loses or gains electrons. Okay, this should be super easy as well. More of a review. So as you gain or lose electrons, you become an ion. Remember, the main thing I want you to know here is that we never change the number of protons. When we're changing charges, that's all due to electrons. We never change protons, otherwise it's going to be a different element, because the whole identification of that element is the number of protons, or the atomic number. Okay? The size of an atom is due mainly to the number of occupied blank that the atoms have. So the size of the atom is mainly due to the number of occupied what that the atom has. And guys, that's energy levels. So energy levels. And all that means, so let's just do beryllium for fun. So it has 4 protons. We're going to assume neutral. So P equals 4. Beryllium's atomic mass is 9, okay, so we'll do 9 minus 4. So then it has 5 neutrons. And then, so that's the nucleus, and then you're drawing the energy levels around it. So these circles that I'm drawing are the energy levels. So beryllium has 4 electrons, and I know that because if it's neutral, it matches the number of protons. So there are 2 in the outer, or this inner circle. There are the inner energy level, okay, right there. And then I have 2 more. Okay, so the main thing I want you to know is the size of an atom is mainly changed by the number of energy levels that it has. So again, how do you know how many energy levels? Is you look at what row it's on. So 1 energy level, 2, 3, 4, 5, 6, 7. Okay. So the more energy levels it has, the bigger the atom. Okay. Now, as you move across a period from left to right, the size of the atom will actually decrease, okay? Many of you think, oh, well, if you're going across a period, it's going to increase because you have more protons, and it's actually the opposite, because those protons have a positive charge that are able to pull in those electrons, so it'll become actually smaller. So as you move across a period from left to right, the size of an atom will decrease. Okay, and this is due to an increased number of protons. Okay, so we can move on. If you're a papoose or yaya, you may want to push pause. All right, so next question is, as you move down a group, the size of the atoms will blank due to a greater number of energy levels as you move down the group. So now we're doing groups. So in all of these size type questions, they're going to ask about the period and the group. So we were doing periods and it increases because the number of protons increases, but now we're talking about groups. So the atom will grow, not grow, but the atom will be bigger as you go down the groups because you're increasing those energy levels, okay? Oops, sorry. So you're increasing those energy levels, so it gets bigger, okay, as you move down it. Oops, the group. So we'll increase due to a greater number of energy levels. Ooh, that's an R. Wow. Let me start over. Okay, there you go. Okay, so next question, the amount of energy required to remove the most loosely held electron from an atom is called the first ionization energy. So in order to pluck an electron away, that's called the first ionization energy. Okay, so that's literally the definition. So to pull an electron off of an atom to make it become an ion or an anion, cation, then you will be completing the first ionization energy. Okay, so the amount of energy required to move a second or a third from an atom is always blank than the amount of energy required to remove the first. So it's always harder to take away the second and third, okay? So it's always harder to take away the second or third, or so the amount of energy is always more. Almost messed up the answer. Okay, so the amount of energy required is always more. All right, so for specific examples, so for potassium, we would expect a large increase in ionization to occur when the blank electron is removed. This is because potassium will have the same electron configuration as blank before the electron is moved. So this I showed you in class. So potassium is here. So you take away one electron and it becomes similar to argon. Okay, so you take away that first ionization, the first ionization energy is, it's going to take energy, but since it's becoming like a noble gas, it's going to be happier like that. So it's going to have all of its valence electrons full, or in other words, in chemistry terms, it's going to be isoelectronic with argon. Once it's isoelectronic with argon and you try to take another electron away from it, that's when that huge jump in energy happens. So the answer, so for potassium, okay, we would expect a large increase we expect a large increase in ionization energy to occur when the second electron is removed, okay? And this is because potassium will have the same electron configuration as, it's technically argon, but I'm going to write noble gas, just for other answers that, on your test, it's not going to be this specific example. All right, so ionization energy will increase as you move blank and decrease as you move blank. So you just kind of have to know the trends. So it will, so it will increase. So it increases as you move this way across the period. And the reason it increases as you move across the period is exactly the same reason that your atomic size decreases, okay? If you move across the period, the trends are changing because you are increasing the number of protons. So if you are increasing the number of protons, those electrons are more attracted towards the nucleus, so pulled in more closely towards the nucleus. And so it's going to be harder to take those electrons away because they are closer towards that nucleus. So ionization energy will increase as you move across the period. And decrease as you move, okay? So as you move down a group, you're increasing those energy levels, those circles on the Bohr-Rutherford model, so you're increasing the size. When you increase the distance from an electron from the nucleus, so let's say this is the nucleus, and we're doing something with 4 energy levels. So we're doing something with, on the level of 1, 2, 3, 4, somewhere here, okay? This is the 4th energy level. So if you're the further you are away from the nucleus, so these electrons get further away from the nucleus as you go down. So here's the nucleus, and as you get further away, it's going to be easier to take these electrons away. Okay, it's easier to take them away the further they are away from this attraction source, which is the protons in the middle. So as you decrease, okay, so you decrease, and decrease as you move down a group. Okay, so the size of a positive ion is always blank than the size of the neutral atom. So the size of a positive ion, another word for positive ion, children, is the cation. Okay, so the size of a cation or a positive ion is always smaller. Okay, it's always smaller than the neutral. Okay, and then the negative ion, so the name of the negative ion is an anion. And those ions are always larger, okay, than the size of the neutral atom. And if you think about it, the nucleus is positive, so we're talking about the cation. The nucleus is positive, and you have these little negative electrons floating around, okay, and they're not like orbiting, they're not planets, they're like electrical negative smears of charge, okay? So if you're a positive ion, so if you have lost an electron, that electron's gone to someone else, okay? So if you are more positive now, these are able to be more attracted to the center, so towards the nucleus. That positive charge the protons are doing that the positive charge of protons are. So these electrons are going to be more attracted inside, so that ion's going to be smaller. They're going to come in more towards that positive charge because now there's less of a negative charge to kind of share that positivity, so they're going to get smaller. Now it's the opposite with the anions. So you still have a positive middle, and you still have these electrons on the outside, but then we add another electron, and all of these other electrons kind of still share the exact same positive charge. So they're going to kind of be able to spread out a little more than the neutral one, okay? So just know cations are smaller, or positive ions are smaller, negative ions are larger. Okay, I need to put that. What is that? That's, yeah, there we go. Fluorine, spelled correctly, has the highest electronegativity with the value of your grade point average, 4.0. Okay, that one's easy. Electronegativity is the ability of an atom to attract electrons to itself when the atom is in a chemical bond. Straight out of your notes. Chemical bond, okay? So if you'll think about it, there will be a group that should stick out in your mind that doesn't participate in these. And so if the test asks you why we don't have electronegativity values for some noble gases, it's because they don't chemically bond to anything. They're noble gases for a reason. They are full, they are happy, they don't borrow, they don't take, they don't give electrons. Electronegativity will blank as you move down a group. So this is another trend, okay? So electronegativity, as you move down a group, so as you go down a group, it's going to decrease. So it's going to not be able to pull in those electrons in a chemical bond as you move further down. And that's because as you move further down, you're adding these energy levels. And so as you add those energy levels, it's going to be further away from the nucleus. So it's not going to attract, the electrons aren't going to be as attracted to the nucleus because of that distance. So electronegativity will decrease as you move down a group. The elements in group blank do not have defined values for electronegativity. That's what we just said. The noble gases, they don't have defined electronegativities. I mean, technically some of them do, but for our 10th grade purposes. And it's because by definition, it's when they're chemically bonded with something. And these just don't chemically bond. That's kind of like comparing me and Kostas Rolotas and Manuli's basketball skills. I just don't play basketball. So like comparing that with me and them is not, I mean, I don't play basketball, so I wouldn't be able to be compared to that. So we just don't compare them. So the elements in group 18, they're actually in group 18, noble gases are, I know because of that. Okay, so the elements in group 18 do not have defined values for electronegativity. And electronegativity will, as you move across a period, it will increase, okay? And that's because you have more protons to suck in those electrons. Again, it's literally the same reason every trend. So increase. You just have to know what it is you're talking about. What is electronegativity? What is ionization energy? What is atomic size? So you have to just know what you're talking about, and you'll be able to figure it out if you know what you're talking about. All right, so these are really, you're going to really see a lot of these on the test. So circle the atom that with the larger atomic size. So the larger atomic size, first we're going to do magnesium or calcium. So the hardest part for you guys will probably be finding these. Okay, so magnesium and calcium, we're doing atomic size. So I know this is the biggest atom. These are the smallest. So atomic size would be getting bigger as you go down and getting smaller as you go to the right. Okay, so the trend is kind of diagonal. They get they get bigger as you go down and to the left. So we're doing, again, magnesium or calcium. Magnesium, calcium. So it wants me to find out the larger one. So calcium is larger in this case because it's the further down. Or the actual scientific answer would be because it has one more energy level than magnesium. So magnesium has, we'll just do quickly like this. So magnesium would have 12 electrons, or 3 energy levels, 2, 3. Calcium will have 4 energy levels, 1, 2, 3, and then that 4th energy level. So calcium is going to be bigger because it has that 4th energy level, okay? And that's why. So calcium's bigger, okay? Ga or Br. So Ga, gallium, or Br. So now basically it's wanting us to compare across the period. So you need to know that as you go this way, you're adding protons. So you're adding that positive charge in the nucleus, so the electrons are going to be pulled in. So it's going to be a smaller atom, okay? So Ga and Br is what we're comparing. This is smaller and this is bigger. So we're looking for the bigger one. So you circle gallium, which is bigger, okay? Next, nitrogen or arsenic. Okay, nitrogen or arsenic. So now we're doing a group again. They get bigger as you go down, so arsenic. Okay, rubidium or strontium, I think is how you say it. Yeah, right here. Okay, so we're side by side. So again, we're doing that whole period trend. So as you go to the right, more protons, electrons are sucked in more. So this is smaller, this is bigger. So Rb is bigger. Okay, they both have the same amount of energy levels. They both have the same amount because they're both in that 1, 2, 3, 4. They both have 5 energy levels, but this one has one more proton, so it's able to pull in those electrons even more. So it's smaller. Okay, Now we're looking for smaller atomic size. That's no big deal. So V or manganese, I think. So manganese and vanadium. Okay. So they're in the same row. They're in the same period. Okay. So they both have. This is 3D. They both have four. What's it called? 4 energy levels. So now we're just kind of looking at the periodic trend, which is proton trend. So V or manganese. So this one's going to be, is it size still? Okay, so it's size. So this one's going to be bigger because this one has more protons to suck in those electrons. So, oh, we're looking for smaller. So this one will be smaller because it has more protons and it's sucking in the electrons. So manganese. Okay, now nitrogen or fluorine. Now we're doing, again, the period, what's it called? Comparison. Okay, so still atomic size, so they get smaller as you go this way, and it's nitrogen and fluorine, so the smaller one's going to be fluorine. It's actually one of the smallest ones. Okay, now we have Sn or Si. So Sn is here, Si is here. Oops. Sn or Si. It's looking for the smallest one. They get bigger as you go down because you're increasing in energy levels. So Si is smaller. Okay. Now the last one for size is rubidium or strontium. Oh, we did it. Okay. Anyways, rubidium or strontium, we already done that one. We have already done that one. It's these two. This one's smaller because it has one more proton and it's able to pull in those electrons. So strontium is smaller in this case. Okay. Very good. Halfway done, children, halfway done. All right, guys, we're going to start the review. It's a different day, and I'm not sure what I've already told you and what I haven't, but we're going to go ahead and get it over with so you can enjoy the rest of your weekend. Now, it says, circle the atom with the larger first ionization energy. So remember, ionization energy will increase as you go up and to the right, and that's because up here there are less energy levels as you go up, and as you go to the right you have more protons, which is making those electrons get pulled in. So these have the highest ionization energy. These would have the lowest because these have more energy levels, which are these little circles on that Bohr-Rutherford model. And so the electrons that we're taking away is actually further from the source that's actually attracting them to the atom. So it's easier to pluck them off. I say pluck them off like they're some kind of little ball, but whatever. Okay, so it says circle the atom with the larger first ionization energy, so phosphorus or sulfur. So on the test, again, guys, I don't know if I've told you, but you're only going to have to answer questions within the same period or group. So you need to know the period and group trends. So with ionization energy, it gets higher as you go to the right. So with the biggest, okay, so the largest. So the largest ionization energy is going to be sulfur because it's further to the right. It has more protons. Next, aluminum or chlorine. There's chlorine, here's aluminum. So chlorine's going to have the highest ionization energy. It'll be harder to take an electron away from it. And you have potassium or lithium. So here's potassium and here's lithium. So the further down you go, the easier it is to take away these electrons. So lithium will have the higher ionization energy. I'm going to zoom in a little bit. Okay, so the next question is oxygen or beryllium. So oxygen's here, beryllium is down here, so it's easier to take electrons from him. So oxygen will be the largest ionization energy. Now we're going to do ion that is larger. So guys, cations are small, okay, because they have less electrons. So that the positive charge in the nucleus is able to pull in those electrons easier, okay? If there's one less electron, okay, if that electron goes away, then the same positive charge is actually spread out amongst the electrons with just one less, so it'll be able to pull them all in further. All right, so cations are smaller than elements, and elements are smaller than anions. Okay, so let's look at this. So F minus 1, we don't really need the periodic table for this. We're really only looking at the charges which the review gave us anyway. So this is F minus 1, and then just F. So if you'll look over here, F minus 1 is an anion, and then we have the element fluorine. Then, so what's it asking? Which one's larger? So it's going to be the anion that's larger, so you're going to circle it. Okay, you have magnesium 2 plus, the cation, and you have magnesium. So now we have a cation and then the element. So which one is larger is the element. Now you have phosphorus, anion with a -1 charge, or phosphorus, anion with a -3. So they're both anions, so that's kind of hard. But the more negative the charge is, the larger it's going to be. And that's because, again, you have this positively charged nucleus attracting a certain amount of electrons. If you get rid of an electron, or if you get rid of an electron, it's going to pull them in further. That's a cation. With an anion, you're actually adding electrons in, okay? So then you have this same positive charge that has to be smeared out against a couple more electrons, and that they're going to be spread out further because of that. It's the same charge being spread out with more electrons. So this is actually going to be a bigger ion. And then here we have two cations. The more positive the charge, the smaller it's going to be. So this is actually going to be larger. Okay. Again, guys, the hardest part is reading that question and figuring out what they're asking. All right, so the next question, circle the atom with a larger electronegativity. So electronegativity is, so the trends again, atomic size, bigger as you go down into the left. So bigger, bigger. Okay, ionization energy and electronegativity, bigger and bigger. Okay, so you need to know the group and period trends. So larger electronegativity, so whichever one basically is closer towards this top right is going to be the largest electronegativity. So we have boron and whatever. Oh, I dropped my mouse. Hold on. Okay, calm down. Okay. Sorry. So I forgot what I was even doing. Boron and Ln. So we have Ln, or I'm sorry, that's In, indium and boron. So we're comparing down the group. So this is higher electronegativity. This is lower electronegativity. Again, if it's down a group, the reason for the change in the trend is always energy levels. If we're going across a period, the reason for every trend is the added addition of protons. Now, larger electronegativity, boron or indium. This is here. Boron's going to have the larger electronegativity. Larger electronegativity, carbon or fluorine. Carbon, fluorine. Fluorine actually has the highest electronegativity out of all of them. Okay. Rubidium and cesium, they're down here, so we're comparing groups. So rubidium or cesium, the higher it is, the higher the element, the higher the electronegativity. So rubidium is the highest. Then we have Sn and Sb. So here's Sn and Sb. They're next to each other. We're comparing the period trend. So it gets electronegativity increases as you go to the right. So antimony is actually the bigger one, Sb. Okay, so the next question says, does lithium or fluorine have the larger atomic radius, and explain why? So basically, atomic radius, so lithium or fluorine. So we're here or here, okay? So fluorine has the, atomic radius? Okay, so sorry. Atomic radius, they're smaller as you go to the right. So lithium will be bigger atomic radius, and that's because as you go to the right, you add protons. So as you go to the right, you're adding this positive charge that's going to pull in those electrons further and further, okay? So basically it says lithium is larger. because it has less protons than fluorine. Okay? So basically, lithium's nuclear charge does not have as strong of a pull on the electrons as fluorine does. Okay, let's go to the next one. Now it says, arrange the following elements as described below. So same period or as group. Again, most of this test is literally you arranging atoms in periods and groups of smallest to largest, largest to smallest, electronegativity, ionization energy, atomic size, ion size. So just make sure you know these trends. These trends are what's going to trip you up on the test. If you get tripped up, you may be making a perfect 100. Okay, so in order of decreasing size, decreasing atomic size from largest to smallest, first one is CFO. So we're basically looking at this one, and this one pretty much every time. And then potassium, lithium, and cesium. Potassium, lithium, and cesium. Okay, so in order of decreasing okay. Okay, so CFO, decreasing atomic size, so this increases atomic size as you go to the up, down, to the left. Decreasing atomic size, CFO, so basically it decreases as you, it increases. It decreases as you go to the right. It's decreasing. So basically it would be COF would be the order of decreasing atomic size. And then down the group, the KLI cesium. So it actually increases as you go up, but we're asking, the atomic size increases as you go down. So basically it's going to be, since it wants decreasing size, you go cesium, potassium, lithium. So cesium, potassium, and lithium. Nick's griping at me because I did not eat the souvlaki he told me to eat. All right, in order of increasing ionization energy. So again, guys, ionization energy increases as you go up and to the right of the periodic table. So across the period, it increases as you go to the right. So it'll be COF again. Okay. But wait, miss, how I thought atomic size goes in the different direction as ionization energy. It does. So on the test, make sure you don't get trolled by the test. This is asking for decreasing. This is asking for increasing. So make sure you have it all straight in the question before you start answering. All right, so now we want increasing going up, increasing ionization for our group. So our group is here, and we want increasing ionization energy. It's going to increase as we go up. So basically it'll be cesium, potassium, and then lithium. Okay, now we're doing decreasing electronegativity. So electronegativity increases as you go up and to the right, but we're looking for decreasing. So that's going to be down and to the left. So the period trend will be right here for a period. Electronegativity decreases as you go to the left, okay? So it will actually be FOC in decreasing. Fluorine, oxygen, carbon, okay? The next is the group. So again, decreasing electronegativity. So electronegativity increases as you go down. I'm so sorry. Electronegativity increases as you go up, but we're actually looking for decreasing, so it's going to be LiK and cesium. Okay. Next page. Okay, so the next question is asking, among the following pairs of atoms, identify the larger of the two. The one that requires the most ionization energy and the one with the lower electronegativity. Guys, again, this whole test is literally, do you know that atoms get bigger as you go down and to the right? Do you know that it gets harder to take away electrons from the elements as you go up and to the right? And do you know that electronegativity increases as you go up and to the right? So they're going to test you all different kinds of ways. Don't freak out. It's literally the same question over and over again. So basically they're asking, here. Which one's larger, lithium or potassium? Lithium, potassium. They get larger as they go down. Potassium's larger, okay? Carbon or nitrogen? Carbon or nitrogen, which one's bigger? Carbon's over here to the left. They get bigger as you go to the left, so carbon. Magnesium or calcium? Magnesium, calcium, it's a group. They get bigger as you go down, so calcium. And oxygen or sulfur, again, bigger as you go down that group, so sulfur will be bigger. Okay, greater ionization energy. So greater ionization energy, this is the highest ionization energy, this is the lowest ionization energy. So greater, so we're looking at, I'm sorry, what are we comparing? Lithium or potassium? Okay, the higher the element is, the higher the ionization energy is. So lithium is the higher ionization energy. Carbon or nitrogen? Carbon, nitrogen. This is the highest ionization energy, and it goes down. So carbon. Are we doing carbon or nitrogen? Okay, sorry, I was thinking oxygen and nitrogen. So carbon will have the lowest one. So nitrogen will have the highest ionization energy. Now we're looking at magnesium or calcium. Magnesium and calcium. Again, ionization energy increases as you go up, so magnesium will have the greater ionization energy. Oxygen or sulfur, here and here. So again, higher the element, the higher ionization energy, so it's oxygen. Then lower electronegativity. So electronegativity also increases as you go up and to the right, but we're looking for the lowest, so don't be trolled by the test. Lithium or potassium, lower ionization energy. So ionization energy decreases as you go down. So you actually have potassium as the lower ionization energy. That is an L, and I'm trying to do a K. Okay, I almost did an L again. Okay, so then you have carbon or nitrogen. Carbon, nitrogen. Carbon, nitrogen. We're doing, what were we doing again? Lower electronegativity. This is high electronegativity. So carbon will actually have the lower electronegativity because it's further to the left. Then magnesium or calcium. Magnesium, calcium, it decreases, electronegativity decreases as you go down, so we actually have calcium as the lower electronegativity. Oxygen and sulfur, here and here, again, same trend, going down, you decrease your electronegativity, so sulfur will be your answer. No big deal. Next question, the outermost energy level configurations of the theoretical elements A through E are listed below. Label what element the electron configuration corresponds to. What does this even mean? Okay, so let me think. I think that it's just 3s2, so that would be 1, 2, 3s2. I'm assuming this is magnesium. Can y'all see? Let me zoom in a little bit. So I'm assuming that would be magnesium, okay? 3s1, 1, 2, 3s1, I'm assuming that's sodium, so Na, ne, that means that's, yes, that's the right answer. Okay, 2s2, 2p6, oh, I get it now, okay, so it's saying that this energy level on the second energy level, it's 2s2, 2p6, so 2s2, 2p6, so that must be neon. They're talking about those circles on the Bull Rutherford. That's what they're doing here. Okay, so basically what they're talking about is you have, so if it is neon, here's the atom, the nucleus, and then we have this inner circle, that's 1s2. Then we have this second circle, which represents both of these, and that would be 2s2, so that's 2. And then 2p6, 1, 2, 3, 4, 5, 6. So it's talking about that second shell. That's a really weird question. Anyways, 2s2 and 2p5. So basically look at 2s2 and then 2p1, 2, 3, 4, 5. That's fluorine. F. And then 2s2, 2p3. So 2s2, 2p3. It's nitrogen. Done. Last question. Then you can go to sleep. Explain why elements with high ionization energies typically also have higher electronegativity values. fluorine, for example. So basically, they don't want to lose electrons, okay? So let's just do fluorine. So fluorine has, it's atomic number 9. So fluorine, I'm just going to do this. It has 9 protons, okay? Then you have this circle, and it has 9 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? 1, 2, yeah, okay. So basically, okay, so basically fluorine wants to be like, they all want to be like a noble gas, but fluorine really only needs 1 more electron to be like a noble gas, okay? So it's going to really suck in that electron. Not to mention it has a high protons here, as far as across the period, and it has a low amount of energy levels. It only has 1, 2 energy levels. So these actual outer electrons are close to this proton, the protons with the nucleus or nuclear charge. You'll see that kind of exchange words like in the test. It'll say protons, or it'll say nuclear charge, or it'll say positive charge, and just know that's all the same thing. So the fluorine, these guys have lots of protons and very few energy levels, so they're really going to hold on tight to those electrons. Those electrons are really pulled in, and so that's really why fluorine, for example, have high electronegativity and ionization energy. It's really hard to pull these electrons out. Now, it's also one of the smaller elements because it's pulled in. You know, it's being pulled in, attracted to that nucleus. The electrons are. Francium has lots of energy levels. It has 1, 2, 3, 4, 5, 6, 7 energy levels, 7 of these circles, okay? So the outside electrons are like way out there. So this positive charge doesn't have as much an effect on this electron than fluorine would on like this electron, okay? So that's really why. So basically, these elements don't want to lose electrons. I'll go ahead and write it for you. These elements don't want to lose electrons because they wish to obtain the same electron configuration. I'm going to go ahead and just write config, just to shorten it up, as the noble gases. Everyone does, but as the noble gases. Okay, that's basically it. So they don't want to lose their electrons, okay, because honestly they only need 1 more to become like a noble gas. So they're not going to give away electrons. That's insane. They're crazy. Okay, these right here, non-metals, they're going to take electrons because they only need to take 1, 2, or 3 electrons to become like these guys. Now these guys, they only have to give away 1, give away 2, give away 3 electrons to become like these guys. So they're not as electronegative, and that's also kind of what affects it. It's not just protons and energy levels. It's not just protons and energy levels. It's also the fact that these guys have 1 electron in their valence shell. They want to get rid of it so they can be like these guys, okay? These are the cool guys. These are the guys everyone wants to be like. They have like, I don't know, cool shoes and hats, and they have like Supreme Jordan sweaters or whatever you guys think is cool. That's these guys, okay? These are like me. Like, I'm totally not them. All right, guys, good luck studying for your test. If you have any questions, you can email me. I love you. Goodbye.